Alrighty, a quick video for you on radioactive decay and half-lives. So I've just got a little definition up the top there to start you off. So the half-life of a radioactive element is the time it takes for half of its atoms to decay. So remember, when something decays, it wastes away. We're talking about it disappearing virtually. In the senior sciences, if you choose to do chemistry, you'll learn more about what this decay actually entails. It's not disappearing because we know that matter is never created or destroyed. It's simply being transferred into another form, or transformed into another form, I should say. So all of these radioactive elements, they decay into something else, but we're not overly concerned just as yet as to what they decay into. So you might have noticed in your worksheet so far that a really common element that you'll come across is this carbon-14. I'm sure that you'll have seen that before. Over on the left-hand side here, I've got carbon with its standard, we would say its most common, atomic number and atomic mass. Remember that the atomic number tells us how many protons there are. So here we can see that there are 6 protons in that carbon atom. We know then that there'll be 6 electrons. This atomic mass number is the protons and the neutrons added together. If we know there's 6 protons, how many more do we need to make 12? The difference between these two is 6. So from that, you know that you've got 6 protons and 6 neutrons in this standard or most common carbon form, or when we compare it to this isotope. Carbon here, we know it's carbon, it's still got the same atomic number, I should say, but the atomic mass is different. In the standard form, it's 12, here it's 14. So here, those 6 protons, we know there's still 6 protons in there. The difference now between 6 and 14 is 8, so there are 8 neutrons. That variation in the number of neutrons in an element is what we call an isotope. So we covered that in previous lessons, but we can discuss that more if you would like soon. This is an isotope. We know that sometimes isotopes can be stable, but in this instance, carbon-14 is an unstable isotope. It's an unstable isotope, so guess what? It wants to decay. And it will do. Now this 5,730 years, this is a really important number for us here because it actually tells us what the half-life of carbon-14 is. So the half-life, remember, is the time it takes for half of the atoms to decay. If we have a certain volume of carbon-14, in this case here, I've represented them with these little green balls. There's 24 of these. So here we've got 24 atoms of carbon-14. It would take 5,730 years for those to decay to half of their original amount. So, in 5,730 years' time, my 24 carbon-14 atoms would only be 12. There'd just be 12 left because we'd have half of them decaying. So, what we can do is graph these half-lives, and we'll see a really distinctive pattern in the amount of carbon-14 as we progress through these half-lives. This pattern that you see will be the same for all radioactive elements. You'll see this really rapid decrease, and then it slowly gets smaller and smaller and smaller. The steepness of it, or the time it takes, the half-life, is different for every element, but if we graph them, we still generally see this same pattern, and we'll show that now. So we've started here at time 0, so right now, we had 24 carbon-14 atoms. I'm going to mark that here in blue on my graph. There's my 24. In 5,730 years, or in one half-life, I'll have half of my carbon-14s left. I had 24, what's half of that? 12. So I need to remove 12 of my carbon-14s. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Take those 2 away. all that I have remaining here is 12 of my carbon-14s after one half-life. I can add that to my graph. After one half-life, I have 12 carbon-14s left. They're decaying. After one more half-life, after another 5,730 years, I'll have half this amount. There's 12 here. What's half of 12? 6. So I need to remove another 6 of my carbon-14 molecules until I'll have just 6 left. I can graph this now again. So we've had, at time 0, we had 24. After one half-life, we had 12. After 2 half-lives, we had 6. After another half-life, another 5,730 years, I'll have half the substance. So I'll be left with just half of 6, which is 3. I can graph that here as well. Now we're getting into the decimal numbers here. Half of 3 is 1.5. I can break up this, say. So after 4 half-lives, there'll be just 1.5 left. Here we're using actual numbers. It's easy to visualize it that way just to start with. But remember that we can also express these as percentages. So here, it's 100% because it's what we initially start with. It's our original amount. Here, it's half of our original amount. So how much is that? 50%. Half of 50% now is 25%. Half of 25% is 12.5%. Half of 12.5%, testing my maths here, it's 6.25%. These percentages you'll see consistently among all different types of radioactive elements. It's this pattern that you see. It's the half-life. Remember, the half-life is the time it takes for half of its atoms to decay. When we have an unstable isotope, they will decay. And carbon-14, remember, is a really important example for us because it actually allows us to date samples. What I mean by that is we all have carbon-14 in our body. We consume carbon-14 because it exists in our atmosphere. When we die, we have a specific percentage of carbon-14 in our makeup. In 5,730 years, we'll have half of that amount, and then half again, and then half again. We can use this to carbon date. You might have heard that term, carbon dating. Carbon date samples of fossils, bone samples, tissue samples, to determine how long ago that organism lived. So it's a really important example. You'll see it a lot in your worksheets and bits and pieces. But remember that this thinking doesn't just apply to carbon-14, it applies to all other radioactive elements as well.